Good morning, ladies and gentlemen. Welcome to the third plenary talk of this conference. My name is Francis Liu. It's my great pleasure and honor to introduce Professor Amir Dembo of Stanford University for today's plenary talk. Amir obtained his PhD in electrical engineering from Technion, Israel, and since 1990, he has been on the faculty of Stanford University. Amir has a very wide spectrum of research areas, including probability theory, information theory, and the theory of large deviations. And together with Alfred Zattoni, he has co-authored a book on theory of large deviations, which is now a classical reference in the field. He is a fellow of IMS, a member of National Academy of Sciences, and the American Academy of Arts and Sciences. So without further ado, I shall leave the stage to Amir, and please welcome me to join me and welcome him.
Okay, so first I want to say it's a pleasure and an honor to speak in the Information Symposium, International Symposium on Information Theory. And I would like to dedicate this talk to the memory of Jacob Ziv, who was influential in helping me, encouraging me, and supporting me upon my graduation from the Technion, when I expressed my interest in moving from my field then of signal processing to information theory, and a few years later when I was moving from information theory to mathematics. And I want to say that I think this success and the thriving quality of this field owes in part to the collegial and encouraging and supporting behavior of senior faculty towards junior one, which I encountered and benefited from in my early academic career in the 80s, both from Jacob Ziv and from Aaron Weiner and Tom Cover, both of whom also passed away by now, who were my mentors as a postdoc. So the talk will be on random graphs, statistical physics, and information. It's quite a lot to capture here. So let me first go over the outline. I will start with a brief introduction to statistical physics, then a brief introduction to constraint satisfaction problems in complexity theory. This will give rise to the use of random graphs to calculate averages. There will be some predictions and theorems about such computational complexity problem coming from predictions from statistical physics, theorems coming from probability theory, especially large deviations. And then I will move on to more specific topic about large deviations, something called naive mean field approximation. And I will talk at the end about low complexity gradient, naive field approximation, and representing a measure as a product or mixture of products. Finishing with a conclusion. I want to say that two things about the outline. First, number 5 and 6 are independent of number 1, 2 to 4. So if you get lost or bored, there is always a recovery point at number 5. Secondly, on the slides on the side, there is a written number, so you can see that some progress is being made. If I'm going too slow, you feel that something is done here anyway. And lastly, I will borrow from an advice I got from Jacob and also from Tom Cover at my beginning youth, that when you give a review of a topic, you don't review the topic, but you only review the part of the topic that you need. So in particular, my review on statistical physics will have no physics. My review on complexity theory will have no complexity. But they will carry the ingredients which I think are interesting to people, to this audience, people doing information theory. And lastly, I want to apologize that actually in my talk there will be really no exact information theoretic result, but at least I will give 2 hints to why this arsenal of ideas should be and might be of interest and potential use to this audience. So let me start with an introduction to statistical physics, and in particular the work of Boltzmann and Gibbs from the 19th century, and in particular the Boltzmann-Gibbs distribution, which will be actually the part of statistical physics we'll care about, and the part that will be the common thread throughout this lecture. So what is a Boltzmann distribution? It's about molecules at equilibrium, and the microstate is a large vector sigma, and I will ignore underlines on all my vectors because otherwise notation will be complicated, but think of sigma as a large vector. And the measure that you are interested in will be an exponential, and in the exponent sits some function called Hamiltonian, which represents the energy of this configuration, sigma. And you normalize by a number z beta, which will appear prominently later in the talk, just to make sure that your measure is a probability measure. There is also a tuning parameter beta, which in physics is 1 over the temperature, to indicate that at high temperature, that is low beta, you allow for a large amount of fluctuations. In particular, if you take beta equals 0, you actually get yourself a product measure. At low temperature, beta goes to infinity, you focus on the minimizers of the entropy. In mathematics, usually people ignore this extra minus sign, and then you move to the maximizer of the function. And at some point, I will move from minimizers to maximizers, not to make a mistake. And the size, there is a size parameter here, n, which is implicit in this notation, but will become soon explicit. So we are talking about a large collection of molecules. In physics, you have about order of 10 to the 22 molecules per liter, so you have a large amount in any reasonable macroscopic situation. The history of this Boltzmann distribution is as follows. First, Bernoulli, in the 18th century already, showed that the heat of gas is related to the kinetic energy of motion of the molecules, and the pressure of the gas represents the reflection of the molecules from the intersections. Maxwell was the first one who did statistical physics by thinking about the distribution of the velocities of molecules of gas. Boltzmann, a few years later, formed the maximum entropy principle, which is well known to people in this audience, and stated that in equilibrium, you will put an equal probability to any microstate consistent with a given knowledge, which is exactly this distribution here, which is marked in star, hence the name Boltzmann distribution. And this is now prominent both in statistics and in information theory, this point of view on measures. And Gibbs, hence the name Boltzmann-Gibbs distribution, later I will move only to Gibbs distribution, few years, 30, 40 years later, wrote an influential book where he said, really, you can do statistical mechanics for large mechanical systems having nothing to do with gases, which was the original theory of Boltzmann. And we will take the point of view of Gibbs even further and said, you actually can deal with these distributions without any regard to physics whatsoever. So that would be my first introduction to statistical physics. And then the second introduction to statistical physics deal with ferromagnetism, or the Ising model. And here the players are Lenz, Ising, and Pearls. This is from the early 20th century. And what they wanted to do is to build a toy model to something like the refrigerator magnet that holds notes on your refrigerator door. And the toy model says the following. The electron spins in a metal has 2 possible states depending on the direction of motion of the electron. And this gives you a rise to magnetic field, which can point up or down depending on how the electron is moving. And the spins, the neighboring atoms in a metal, typically align, especially at low temperature, but at high temperature they stop aligning because there is enough kinetic energy to bypass this potential force. And what gives rise in the toy model, you have now arrows up and down, like here. These pictures are taken, by the way, from the internet, not my invention. and you get magnetic field if they are all aligned in one direction, and if they are randomly aligned, then of course you have no magnet. And here is a picture of a simulation, again from the internet, of Ising model. You have a lattice of spins. The atoms in a crystal are sitting on a lattice. This is a two-dimensional picture. The spins are plus or minus 1, representing up or down spins. And you see that at a temperature, green and red here are indicating the type of the spins. And you see that at high temperature, T much bigger than the critical, they are kind of randomly, the colors are randomly mixed. And at low temperature, one of them become dominant, either the green or the blue, because it's much better for them to be all aligned. And at a critical transition, phase transition at critical temperature Tc, or some parameter beta C, 1 over Tc, you see kind of an interesting long-range behavior, and you can study this mathematically to death, and also physicists are interested in the phase transition. The story of the topic, so let's make a mathematical model out of it. What is the Ising model? You have a graph. In our example, it was the lattice, V, a finite graph or an infinite graph, and some edges. And then there are spins, sigma I, which takes two values, -1 or +1 for up and down. They like to be aligned, so the Hamiltonian will sum over all the edges in the graph, the product of the spin values, which if they are both plus will be plus, both minus will be also plus, and otherwise will be minus. Then we put a minus, the minimal value of the Hamiltonian will be when they are all plus or all minus. Beta here, the parameter in front, can be positive. This means ferromagnet, like what I described to you. But you can also put it to be negative, in which case they actually don't like to be the same, and it's not going to be a magnet. So Lenz in 1920 invented this model, decided on this Hamiltonian with a Boltzmann-Gibbs measure as a toy model for magnetism. And he gave it as a problem to his PhD student at the time, Ising, who ruled out phase transition when the graph was one-dimensional correctly, and speculated based on this that the same applies in all dimensions, got a PhD thesis on that, and also got his name on the model, which probably should have been called Lenz model, but this is the usual mistake in assigning credit in mathematics. And 9 years, and all interest in the model completely died out because Ising speculated and convinced other people that there is no phase transition, so it's not going to be a good model for magnet. But 9 years later, Perlis did a calculation and showed that there is a phase transition in Z2, and now we know that there is a phase transition in any dimension except dimension 1. So moving from dimension 1 to 2 was not a great idea without checking it. Okay, now what is modern statistical physics? Modern statistical physics goes, first of all, beyond ZD, and second of all, moves to spin glasses. Spin glasses are materials where the interaction is no longer all the same or all against, but some would like to be the same and some would like to be not the same. And the point of view of this modern statistical physics was first in order to model glasses. Glasses are non-crystalline solids, and because they are non-crystalline, the atoms of the glass will not necessarily sit on a lattice. And secondly, in a glass, as we know, there are impurities. This is what caused glasses after many years to not be flat and nice and clean as they are in the beginning. And a spin glass is a disordered magnet, which is supposed to be a toy model for analyzing glasses. So what is a spin glass? It's going to be a Boltzmann distribution, very similar to the one we had before. The Hamiltonian is a sum over the edges of products of sigma I, sigma j's. The sigma still takes a value -1 and +1, but the interaction between them now has a random sign, jij. In principle, it can be a complicated function, but if you don't know what it is, you might as well make it random. Now, what you would like to do, you would like to study this kind of spin glass when G is a subset of Z2. That will be, or Z3, that will be physically interested, but this is called the Edward-Anderson model. It's very difficult, even up to today, even for physicists to figure out what happens then. As a toy model, a simple problem was devised by Sherrington and Kirkpatrick in 1973. They said, what can be simpler than a lattice? Let's take the complete graph, everybody connected to everyone, then we have a much better chance of solving it, because also Ising model on a complete graph is trivial. It's called the Curie-Weiss, and it's done by large deviation. And then they solved the problem of the Sherrington-Kirkpatrick model rigorously, published it, and this solution they gave was wrong. The solution was wrong, a lot of literature came by, and after 7 years, Parisi came with a predicted structure called the Parisi formula for SK, for which he got the Nobel Prize recently. This was all based on the replica symmetry breaking, which is really far from mathematical analysis in general. Even worse, if the graph is a sparse graph, this is called the Viana-Bray model, which came shortly after Sherrington-Kirkpatrick model, and this is still up to today also quite complicated to analyze. Okay, where do we get to computational complexity? Now I shift gears. We are now in part 2 of the talk. Computational complexity and constraint satisfaction problem. In complexity theory, the holy grail is whether P is equal to NP or not. What this problem is, it's a decision problem. You have a formal question of yes and no answer. And depending on an input of varying lengths m, and think of m as being very large. And the question is, example, is there an assignment of a Boolean variable for which a given Boolean formula is satisfied? This is called the SAT problem. Decision problem is in a class P if it's easy to solve it. Easy to solve it means that you can devise an algorithm that will answer correctly at number of operations or steps which grow only polynomially with m. So m is large, you can still do it with a bigger computer. It is in class NP if there is a simple algorithm for checking whether somebody proposed to you a solution, whether it is a solution, but you are not sure whether there is an algorithm to actually find the solutions. And Cook in 1971 showed that if 3SAT, which is this assignment of Boolean function in a canonical form, is polynomial, then P must be equal to NP. But this, as you can see, is a conditional theorem, and the holy grail is to figure out whether P is equal to NP or not, for which it suffices to show that 3SAT is in P, or not. Right? And you will get the Clay $1 million prize by resolving this. I'm not going to do it in this lecture, if you were considering that. And there are many CSP which people in complexity theory worked then, not hard, but worked to show various other problems, not just 3SAT, where if you decide on this problem, if it's polynomial, it will imply that the whole family collapses. Now the expert believes that P is not equal to NP, so there is no, all these problems are considered hard. And we will talk here specifically on 2 of them, independent set and max cut. Not because they are more interesting, but because, or more important, but because they lend themselves easily to representation by statistical physics, and therefore to carry the theme of this lecture. Okay, so the independent set model. What is the question? You have a graph V, and the question is there a set S of vertices in your graph of a given size K, where there are no edges between those vertices. There can be many edges, but not between 2 vertices of this set. So here is an example of a graph, and here is an example of, in purple, of an independent set of size 7. You can check that if you start at any of the vertices marked with purple, and you look at the edges coming out of them, hopefully they do not connect to any edge in purple, or else I have a typo. So this is an independent set of size 7. And the question in CSP is whether this is such an independent set, or more generally, find the largest independent set of a graph where the graph is very large. And here is a model from a statistical physics point of view. This is called the hardcore model. You put now your objects are 0 and 1. 0, the independent sets are sets of vertices where the sigma, the variable is 1, occupied vertices. And what is your Boltzmann measure? Your Boltzmann measure involves here a product term which has 1 minus sigma I sigma j over all the edges. So if any edge has both vertices occupied, this indicator becomes 0 and kills the whole product. Otherwise, its contribution is 1. And if you want to to make for a larger independent set, you put a sum of sigmas, trying to occupy more, with a positive number beta. So this will encode independent sets with no neighbors occupied. In particular, the partition functions, the normalize, can be checked to be just a sum over the independent sets because everybody else will be 0, e to the beta times the size of the independent set. In particular, if you look at z of 0, you just count the number of independent sets of the graph. And if you look at the largest size of independent set for G, which relates to the problem in complexity, this is what is called the ground state energy. What is a ground state energy? You calculate the log of Z beta, you divide by beta, and you take the limit as beta goes to infinity. This will just give you the maximum of what is in the Hamiltonian. In our case, the maximum of the size of S, where S is an independent set. So the decision theorem, decision problem is really to calculate the ground state energy of the hardcore model. That's a connection to statistical physics. Here is another problem in complexity, and again, related now to the Ising model, which I gave you in the first problem. This is now the problem of max cut. Here is your graph, and you are trying to cut the graph to 2. Here is my notation for a cut, the red line. And what does it mean, a cut for me? I assign +1 to all the vertices on one side of the cut, -1 to all the vertices on the other side of the cut, and the size of the cut is therefore the number of edges, with one variable being plus and one variable being minus. And you can easily calculate that if you take twice the size of the cut minus the number of edges, what will get you? You will get 1 whenever you have a pair with +1, and -1 whenever you have a pair with -1, and this will be h of sigma for an Ising on a graph. So if you want the max cut, what you need to do is to calculate the max of the cut over all the subsets. You try to cut it in such a way that there are lots of edges here, and twice max cut minus E, minus the number of edges, is a ground state energy for an antiferromagnetic Ising, because now you are trying to make a lot of the -1 and 1 in order to maximize the cut. If you wanted min cut, it will be the ground state for an Ising model, but the min cut is quite trivial. You would just take in the set S everybody. That's not very clever or interesting to do. So solving the max cut problem corresponds to finding the ground state energy of an antiferromagnetic Ising. And as you can see, this is probably also a hard problem. Okay, so this was all about complexity theory, but there was nothing random in the talk yet. But these constraint satisfaction problems are believed to be hard, but the question you can ask yourself, are they really hard? Meaning, maybe there is only one esoteric graph where they are hard, but if you choose graphs typically at random or typical graphs, the problems are quite easy to manage. So for that, you need to understand what do we mean by a typical graph. And this gives rise to the story of average complexity for random sparse graphs, and in particular to random graphs. And the random graphs we will use in this lecture are two types, the Erdos-Renyi random graph and the random regular graph. In both cases, we take a large graph, n vertices, and we fix, in the first case, we fix a number of edges to be m, and then we choose all the graphs to be uniform. So all the graphs are possible, each with equal probability, but we just fix two parameters, the number of vertices and the number of edges. This is the Erdos-Renyi graph, and you can calculate the average degree is 2m over n, because you have exactly two vertices participate in each edge. The random regular graph, you put more constraint. You keep the number of vertices to be n, but now you want all the degrees to be exactly this gamma instead of just on the average gamma, and then you choose a graph uniform among all the graphs with this property. And in particular, we will take typically gamma to be order 1, or definitely gamma which is not linear in n. So these are called sparse graphs. And we will want to study constraint satisfaction problem for these graphs of this family. So random regular graph is actually locally a regular tree. This is a nice observation which will help us a lot. Now, what does it mean to be locally a tree-like? It means that a local neighborhood of a uniformly chosen vertex converges to a random tree. possibly random, but converges to a tree. It's not saying that every vertex has a neighborhood, all the neighborhoods are tree, because then the graph will be a tree. At some point you must meet loops. But it means that for most vertices, it will take a long time to find the loop because the degree is not growing like n. So in particular, let me show you a simulation. Here I choose a point. This is a 3 regular graph, randomly chosen 3 regular graph. I did not plot this picture. This contributed by Nike-san a few years ago. So I choose a point at random here, let's say, and then I look at I have 3 neighbors, and then I look, I have 3 neighbors to them, and I can continue for a while until I find a circle. So in particular, if I isolate this, what I say is that if my graph is regular graph with degree gamma and n vertices, for large n, it converges in this local sense to the regular tree with degree 3 to each one. Okay? And this gives rise to many predictions for constraint satisfaction problem on such graphs coming from physics. And these are mostly attributed to Hans Bethe, who lived in the 20th century, who did not work on constraint satisfaction problem, but gave prediction to model in physics that looks like trees or that can be analyzed in this manner. And his predictions have been moved later by more modern physicists to the problem of constraint satisfaction problem. So I will go over 3 different predictions. One is the so-called mean field equations. And this is also the source of an algorithm commonly used in statistics and in AI called belief propagation. And what Hans Bethe said, that you can find order of n equations that determine the local marginal in a large system. And this is good because in general, in a probability measure over n variables, you will have 2 to the n type things to do. And here you can characterize everything by n things. And how do you do that? Let's look again. We re-express a Boltzmann distribution instead of exponential, a general functions over the edges of pairs of spins. So we have this more abstract, more general Boltzmann distribution. Now, imagine that for a moment that our graph was not a tree-like, but exactly a tree. If the graph is exactly a tree, once you take out one edge, the 2 parts of the tree get disconnected. If they are disconnected, this measure becomes a product of 2 different measures, one for each side of the graph. So you can calculate the marginal law of one variable on one side, let's say sigma I, on the graph after you remove the edge ij. And this relates to the part of the graph that does not involve j, but involve I. And you think of it as a message that vertex I is sending to vertex j, telling it, okay, my distribution of my spin from my side of the graph is such and such. And then, if it is a tree, you can check by algebra that you have exactly these identities. You take all the messages coming from all the neighbors of I, which are not j. You multiply them by the factors which appear here of I and L. You sum over the possible dummy variable that you send, and this, after a simple normalization, will be the message going from I to j. And if you write here equality, put here iteration n and put here iteration n plus 1, that's a belief propagation algorithm. So in particular, if you had a tree, then the measure, the Gibbs measure, can be written can be characterized completely by the fixed point solutions to the belief propagation algorithm. Now, if our graph is near a tree, we might have the philosophy of approximate it by using, for local marginals, those solutions that come from imagining it's a tree, even though it's not a tree. So it's going to be an approximation, but when n is large, maybe this approximation is quite good. So that's the idea of beta. And you can carry it out to calculate also beta Gibbs measures and free energy density. So let's think now of a graph sequence, like in our constraint satisfaction problem, with a large n, which is tree-like. Then we can look at the partition function Zn, which is the sum of our products. And if our products are simply 1 when we satisfy the constraint and 0 otherwise, then Zn is simply counting how many solutions we have to the constraint satisfaction. In particular, we are interested whether Zn is greater or equal to 1 or 0. One way to see it is to calculate the asymptotic growth of the number of constraint satisfaction problem. This is called in physics free energy density, and it's given by 1 over n, the log of Zn, the limit. Assuming the limit exists, let's call it phi. The value of this limit and its dependence on beta and other parameters give us information on the qualitative behavior of large random or large problem instances in our random situation or typical situation. And the beta prediction says the following, that you can actually write this number, and in particular you can predict when you move from Zn equal to greater or equal to 1, when phi is greater or equal to 0, to phi which is minus infinity, corresponding to Zn which is 0. And this is an explicit functional that you can write. It will take me a screen, so I'm not going to do it, but it's an explicit functional you can write, which depend only on your limit tree. It does not matter what graphs you have. And it's an explicit, as I said, and the argument of this functional is a candidate for our measure. And the candidate for our Gibbs measure, when n is very large, behave like this. It has what is called the beta Perle structure, meaning if you look at any collection, finite collection of variables, u, and you look at the configuration only of those and disregard the rest of the graph, your measure will correspond to the weight coming from here of the configuration, which means really that you are locally satisfying your constraint, times a product law on all the vertices on the boundary that tells you what the rest of the graph tell you about the possibility for the spins at the boundary. And this is called the beta Gibbs measure with entrance law H star in particular. And this particular H star must be, this is a prediction, must be a fixed point of the belief propagation update equation based on the heuristic for A, which I had in the earlier slide. Third prediction coming from statistical physics, which may be even more interesting from a point of view of computational complexity. It says that the hardness of the problem correspond to set of solutions splitting into lumps. And here is a picture, kind of a very rough graphical pictorial picture of the space of solution. You have a certain degree of difficulty. Degree of difficulty is a number of constraints per number of variables. The more constraints you have, the harder it is to solve the problem. So in particular, in independent set, alpha, this parameter, will be the ratio, the fraction of occupied vertices. You're trying to get it as large as possible. In satisfaction problem, it will be the ratio between the number of constraints, Boolean constraints you put, to the number of variables. And here is a picture that you see, believed to exist in a variety of different problems. In the beginning, the space of solution is not a ball, but is well connected. Near every solution, in a short distance from it, you will find another solution. In particular, if you start with a solution, once you make few local moves, you can kind of go over all the solution space. And this suggests that finding a solution should probably also be quite easy to do. And indeed, algorithms work very well in this part of the space, of the parameter space. Then there is a transition at a particular number called alpha D or alpha dynamic or alpha shattering, where suddenly you shatter into exponentially within n many clusters. Near points, variables, solutions in each cluster are nearby, but the ones between different clusters are macroscopic distance from each other, order n. So you need actually to make n changes to go from one cluster to another. This suggests that the problem will be quite hard. Then there is another phase transition, alpha C, where things are even worse, because suddenly your exponential number of clusters drop down to an order 1 number of clusters, which occupy a very small part of the space and are separated from each other. And then there is a last phase transition, which is a one of interest in complexity theory, after which there is no solution. Now, because of all these things come from statistical physics, they actually come with precise prediction for these three numbers. Which model has which numbers and what the numbers are. So there are nice formulas, except that they are non-rigorous because they are using replica symmetry breaking strategy to come to find them. Okay, so now I move to probability theory and tell you a few mathematical results about this story. So we are now in part 4. Part A. Let's look at max cut for large degree. There was a conjecture in statistical physics of Dembo and Bochner from 2010, which was resolved in a paper with Montanari and Sen in 2017 with me, based on statistical physics. And what they said is the following. If you look at the ground state of the max cut problem, it's a problem remember, this is a problem in constraint satisfaction problem in discrete combinatorics, really. And the answer is this is a trivial part. This is a number of edges divided by 2. Number of edges is n gamma over 2 divided by 2, n gamma over 4. Everybody knows this factor, no problem. The next factor was of much interest to people in combinatorics. It was known that it behaves like n square root of gamma, but the coefficient in front of square root of gamma was unknown, and there were quite a lot of papers, sequence of paper by Noga Alon, Bolobash, and others, who were improving the lower bound and upper bound, trying to close the gap. And the conjecture of Dembo and Bochner is that this number is actually the ground state energy of the Sherrington-Kirkpatrick model given by Parisi formula. But Parisi formula is an explicit formula coming from statistical physics, but it's quite complicated, and it has nothing to do with combinatorics, I assure you of that. So if you are trying to get it by combinatorics means you will never get it. This I'm pretty sure also. Now, the Parisi formula and this limit was proved that this limit exists only in 2002, 20 years after Parisi proposed it, by Guerra and Toninelli, and 4 years later, Talleyrand managed to prove that this limit, which exists by subadditivity, that was a contribution of Guerra and Toninelli, is actually equal to the number predicted by Parisi. And this was a monumental work of mathematics to do this job. Now, building on giants, we could prove that the result in the max cut problem, the next leading term will involve the coefficient P star, which was quite surprising, at least in the non-statistical physics community. And this was 4 years after Bayati, Gamarnik, and Tetali used subadditivity to prove that this limit exists without finding what it is. So this was one example of a mathematical success. Here is an example of an even more remarkable and harder mathematical success by others, I may say, so I can say safely it's much harder and more impressive. And this is determining the saturation, the satisfaction transition where independent set on random graph is satisfied or not. This was a contribution of Ding, Sly, and Sun from 2016. And they proved that for a regular graph, the maximum fraction of vertices occupied by an independent set has a sharp threshold. Sharp threshold means with probability close to 1, you will find one if alpha is less than alpha s. Probability close to 0, you will find one once alpha cross below alpha s. So you can go from 0 to 1, like in information theory. And this transition point matched the prediction coming from what is called one RSB, one replica symmetry breaking prediction. And in this context, what is one replica symmetry breaking? It has a nice meaning to the original problem. It corresponds to doing, again, a limiting Gibbs measure whose structure is similar to the one I gave you before. The weight, the constraint in every given neighborhood, multiplied by an entry law, messages coming from all the other parts of the tree. But what is the difference now? The messages which before were numbered. Sigma was just 0 or 1, so h was just a number, the probability of sigma, probability between 0 and 1. Now, these are random variables. They are random probabilities. And these probabilities are chosen according to a law, Q star, and you find the law by doing a belief propagation, this algorithm of belief propagation, but not in the space of numbers, but in the space of probability measures or numbers. So you kind of elevate, go one floor up, and then do your belief propagation. And this also has a meaning. This is a replica symmetry prediction if you are not counting solutions, but you are counting solution clusters. Instead of saying number of solutions go from 1 to 0, you can say number of solution clusters go from 1 to 0. and solution clusters are replica symmetry, whereas solutions are replica symmetry breaking. All that you need to do is to justify what I just said. The paper is 100-page long, and the pages are complicated. It's not just 100-page long because I like to write long paper. Anyway, it's a very challenging problem, but it was resolved. Let me go to an easier problem, much easier problem, for which you can do a lot, and which is actually of interest and has been used in information theory. This is a problem called XOR-SAT problem. Now you're looking at a system of m Boolean linear equations, each having k input, and you're trying to satisfy them. This is actually a complicated way to write a system of linear equations with bits. And here is what is called the factograph corresponding to it. I will not go over this notation. But the point is that a XOR-SAT problem corresponds to using low-density Perry-Check codes on a binary erasure channel, and you can modify the type of code ensemble, so it will not have exactly k input. You can shape them, you can change the channel, and so on and so forth. And there have been a lot of literature on this. From a statistical physics point of view, this is an easier problem. It's an easier problem because you have this linear algebra, also on a finite field, which helps a lot. For example, it makes all the clusters of the same size automatically because it just the number of solutions of a certain, it's a rank of a linear algebra problem. And in a paper with Montanari in 2008, which follows a work by Amroui, Montanari, Urbanker, and Richardson in 2005, we worked on finite size scaling. What is finite size scaling in this business? The prediction alpha d come from statistical physics, but can be mathematically rigorously done. And this is, and you are interested in this point, that will determine the probability of error, but you want to work with modest n. You don't want your n to be the number of electrons in the universe. You want n to be 100 maybe for random code. And for that, you need to do a lot of scaling. You need to go from statistical physics, which is like law of large numbers, to next correction term, which is CLT, which was done by Amroui et al. And then you need also to correct with a pre-exponent. But because the problem is easy, you can do it with classical probability, and that's what was done here. So this is just to show you that in one example where information theory is relevant, and I will conclude this part of the talk by saying that there is an extremely nice book of Mazard and Montanari from 2009, which tells you a lot about constraint satisfaction problem, information theory, and statistical physics, and also coding theory. And there is a paper that I wrote with Andrea Montanari from 2010, a review paper of what was known in 2010, which is not everything, but including this part, for example, which is essentially a small subset of what is in the book, but the subset which is mathematically rigorous, and not the information theory part. So this book has information theory, lots of predictions from statistical physics, and mathematics. This survey paper has only the mathematics, so it's shorter. Okay, and I move now to the next topic. And as I mentioned, this is number 5. As I mentioned, if you lost me, or you are bored, or this is not of interest, you can recover. Maybe you lose me again, but you have 2 chances now. So I'm talking now about nonlinear large deviation. The name is nonlinear large deviation, but I think the name is really a bad name. And since I share at least 50% of the name, I can say that safely. So it's about large deviations and naive mean field approximations. Or if you want, from the point of view of information theory, is what to do when you want to do something like the method of types, but the method of types is completely irrelevant to the problem. So what can you do? So let me explain. First, let's start with the large deviation principle. So this is going to be a slide, crash course in large deviations, really crash course. Okay? So we have probability measures, sequence of probability measures, mu n. They all sit on the same space, x. The large deviation principle has 2 parameters in it, a rate and a rate function. And it says that really the log of the probability of sets has to be decaying with a rate Rn, and in front of the rate Rn is a function, explicit function of your set. And this function of the set should be the minimum of a function defined on points over all the points in the set. And this should be true for many sets in your space. That's the large deviation principle. And what is missing here is what this wiggle means and what sets can we take. A rigorous formulation of this statement, due to Varadan in 1966, is analogous to convergence in law, convergence in probability. You take the log, divide by Rn, and you want it to be equal to minus j of E. But this you cannot do for all the sets. So you say, okay, I want it to be greater, this limit is greater or equal to minus j of E when E is an open set. It's less equal if E is a closed set. And if I'm lucky, and I have a set which is both open and closed, or the value of j for the closure and the open and the interior are the same, then I can make it equal and say that I got the limit to be equal. And the intuition, if you want to state it more colloquially, is just to say that mu n has a density e to the minus jx times Rn plus a correction term in the exponent, which is much smaller than the leading term when n is large and x is fixed. So you got yourself the leading rate of decay for your probability measure. Now, the large deviation requires, this is a mathematical fact, it requires mu n to strongly concentrate on compacts. In a finite alphabet, for example, this is not a problem at all because the space already is compact. If you have an infinite alphabet, then you run into trouble, which Neri, for example, Neri Merchav explained to us on Monday, that you truncate or you quantize, and this is one way to get yourself into business. But in principle, in general, you want to be concentrate on compact. This is called in large deviation theory exponential tightness. And tightness here is not in the sense that Neri meant, but in a much weaker sense, just to say most of the probability should be sitting on compact sets. And it's easier to do large deviation in principle if your metric is coarse. If the way you calculate distances is very rough, it's a weaker statement, but it's a statement which is easier to get because you have less open sets and less closed sets, so it's easier to do stuff. It's impossible if you take the metric to be too fine. A good example is try to do large deviation in a metric of total variation convergence, where your variables are discrete, but they converge to Gaussian. So the distance will be not going to work. So often, and that's really an issue, it's not even clear what the space should be. An example, running example to keep in mind, think of a law of a random graph of n vertices. Well, a random graph of n vertices is not sitting on the same place. Every time you add a vertex, it's not in the same place. So you need to do something to your graph to make it, put it in the same space. However, by now there is a rich theory around large deviations, especially for weighted average of independent variables, also for nice Markov chains and Gaussian processes. In particular, nice stuff coming in time series problems or information theory problems or statistics, you can do large deviation for it. But if you work on graphs, your life is miserable because it's not on a line. This is just a remark. Okay, so let's talk about the method of type for a moment, which really in large deviation is called Sanov's large deviation principle for IID. Here we take a specific case. We take mu n, the probability distribution of the empirical measure. We put an atom with probability 1 over n to each of the points xi. Our xi's are independent, identically distributed random variables of some marginal law. And we are looking at this object, which is a random probability measure on y. Now, method of types correspond to the case where y is a finite set. So we are working on a finite simplex. This is just a nice random vector. And we can use any topology we want. It's clear they are all the same, and there is no problem whatsoever. Sanov, in 1957, proved that this situation, you have the large deviation principle, the rate is going to be n, and the rate function is going to be the relative entropy or the Kullback-Leibler measure, which is given by the sum of nu x log nu x over mu star x. This is in a case where y is a discrete space, and otherwise you just change it to an integral. Now, the key identity in proving this is an identity. The key to proving this result, actually, is an identity to partition functions of Gibbs measure. And this is the part that I want to take from this slide towards the rest of the talk. And the log of the partition function can be written as a variational problem, the soup over all probability measures of the integral or the sum of h times the candidate nu. Nu is the element of my optimization, minus the penalty I pay is a relative entropy. So if I put nu equal mu star, the payment here is 0, but then I don't get too much here. I just get the value of h under mu star. If I want to increase it, I need to pay a penalty. And z of h, I remind you, is just the integral of e to the h times my reference measure mu star. And the way you prove this identity is simply by easy calculus. You just write this object here as a sum, you write this as a sum, you try calculate Lagrange multipliers for the degree of freedom you have for nu of x, and you just solve it, and you get a nice solution, which is an exponential measure, and you get this identity. So this identity is very easy to derive, very powerful, but maybe not doing much. Okay. So now let's go to our talk, go back to our Gibbs measure. So we are looking at a Gibbs measure of IID Bernoulli's. Let's allow p depending on n, 0, 1 to the dn. I could have taken minus 1, 1 to the dn if I want. I allow d to depend on n in some manner. D goes with n to infinity. If I think of a graph, maybe dn is n choose 2 for the edges. And I have Bernoulli variable. This is going to be the Erdos-Renyi random graph. And suppose I have a nice function h from yn non-negative, and I know that the tail probabilities of this function decay at a rate e to the minus rn. So I already know my rate, I know what I'm aiming for, but I don't know the coefficient in front. And that's my goal, to find this coefficient, the rate function. So what do? I consider first a Gibbs measure on yn instead of my original problem, meaning I look at a function e to the rn times h times my original measure. Why do I multiply here by rn? Because I want the weight factor to be comparable to the tail behavior. So I can move from the typical to the atypical, and I have a nice fight between them. And the partition function is, of course, going to be the normalizing factor, which I wrote here. Now recall the relative entropy, which I wrote here. Now everything with n's, and our key identity from the previous slide. The naive mean field approximation says, what about trying, this is not going to help me because this space is huge. It consists of all probability measures over exponential discrete set. I'm not really helped by that. My problem really here is I cannot calculate this function, so the problem will not be solved by that. But maybe I'm lucky, and actually there is a naive mean field approximation, meaning the log of Zn is approximately given by the soup only over product measures. Only I keep the independent structure. Suppose in mun I had independent structure, I might hope that even after optimization, roughly I keep the independent structure. In this case, if the log of Zn is leading term this one, and then there is a small error, I never said that it's the same, but the error is much smaller, then this quantity I can actually solve explicitly. It's not very difficult because it's a relative entropy between two products. You can write it as a sum. You can solve the optimization problem step by step, and you get it in this form. It's written as a supremum over parameters now which are, instead of 0 and 1, they are continuous between 0 and 1. And you write your function h not at the discrete point, but at the intermediate point q. And the rate function, the penalty, is just the sum of the binary relative entropies at the parameters that you are doing here. So this is a much easier optimization problem than the one you had before. So what did we do? We split the problem of estimating the partition function into guessing that it's going to be of a nice form. And then we still have a variational problem on a large space that we can separately try to solve analytically at the second stage. So we split it like in information theory. Instead of trying to get to a single letter description, you try to get first to a nice big description of blocks and then work out the algebra or the analysis of it. So you split the space the problem into two parts with the hope that this will make each of them less formidable. Now, remember, the problem originally started with large deviations. How are large deviations connected to Gibbs measure? Very simply, suppose you wanted to control the indicator of a function a function being bigger than L. What you do, you just take a function e to the Rn h, which is a smooth approximation of an indicator. If you try to write an indicator as an exponential, it's a function h which is 0 when the indicator is 1, and minus infinity when the indicator is 0. So you make it 0 when it's 1, and then minus a when it's supposed to be minus infinity, and go between them linearly, so you have a nice function. And then the log of the tail probability is really becoming the log of the n, because only the indicator will contribute. And this will just be, after you write this equation, it will just be minus the infimum now instead of a supremum over all the penalty among all the possible parameters which will satisfy your constraint. So this is an expression that you can later try to work out and get a more explicit result. Okay, so with Churov-Chatterjee in 2016, we proved that this approach of naive mean field approximation, approximating by product, is valid whenever your functions, f or h, have low complexity gradient. What does low complexity gradient mean? This might be of interest to people in this audience. It means that you can approximate the gradient over all the points in the space by a net of size little order, exponential little order of Rn. It really means that you can transmit your gradient information in less than Rn bits, or quantize it in a nice way. And once you have this, we proved that this implies these two results I mentioned to you. It implies a partition function leading term can be written as this nicer variational problem. You can later on try to work in situation to get a nice single letter expression, or the tail probability can be written as this other variation problem. What is left for you after the theory in terms of application-specific tasks? Two. First, you need to verify the log complexity gradient condition, whether you are lucky or not. And secondly, if you are not happy with this big variational problem, you need to actually divide this by Rn, because that's the leading term you want, and show that this will converge to an explicit function, which is a function of a single letter, or a nice variational problem. And this is a way to replace using the method of types in situations where you do not, where the point is the function h or the function f are not written as function of the empirical measure. So I cannot directly use method of type. For example, in graphs. And this was very successful in calculating large deviations for counting subgraphs in a sparse random graph. And why would you like to count subgraph in a sparse random graph? Because this is really related to Gibbs measures of models which are called edge triangle and variation of such, which are supposed to model social networks, where you say that if I am your friend and somebody else, and if I am a friend of A, and B is also a friend of A, there is a larger likelihood that I will be a friend of my friend than of a random person. And why it's a random graph? Because if the population of the world goes like billions, I don't have billions of friends. Even if I'm a very friendly person, I have a finite or growing slowly number of friends. And you can see this in a paper I wrote with Nick Cook recently, put on arXiv, when a lot of citations about earlier work on this, which all use this theory in order, and this stuff, in order to go successfully better and better on such models. Now, the theory, by the way, if you are not happy with binary, but you like Gaussian channels, Gaussian stuff, this theory extends very nicely to Gaussian setting. There is a great and elegant paper of Eldan that actually used Gaussian problems in order to improve what we did for binary. So it's a case where Gaussian can do with Bernoulli. But I will not go over this paper. Instead, I will use a few moments just to say that last minute, just to say that low complexity gradient give you mixtures. What is the situation here? We take a space, which is a product space, like the previous one was product of Bernoulli, and suppose there is a partition which less than less than exponential size partition of the space, which induces a low complexity gradient range. That is, if you look at cells of this partition, the gradient is more or less constant on cell. And you don't have too many of them. That's one way to get low complexity gradient. Then it means that the Gibbs measure is going to be well approximated by a mixture of not too many product measures based on cells of P. This is a very nice paper of Tim Austin from 2019. Let me tell you what the paper is, because you would like this paper, I'm sure. Here is what the paper says. First of all, the condition of low complexity gradient, what it means. The following, it means that if you write the sum over the element of the partition of your Gibbs measure times, this is a distance in relative entropy between the Gibbs measure restricted to this set and the product measure. This is going to be little order of n. In general, this relative entropy is order of n. Being little order of n means that you have less mixtures than in general. And what is more interesting, I think, is the proof is just information identities and inequalities. The proof is very short and has nothing other than information theory in it, even though there is no information theory in this result, really. And what is the proof based on? It's based on the dual correlation coefficient due to Hahn, which this is a Shannon entropy. It's a Shannon entropy of n variable minus the sum of the Shannon entropy of one variable given all the rest. This quantity is known to information theorists and probabilists to be non-negative. And what Tim is doing over one page, I think, not more than that, he derived a modified novel chain rule for relative entropy, not your chain rule, but also a chain rule, not the chain rule you might know, but another one. He combined it with the Gibbs identity that I mentioned to you before to show that it's actually to equate, he says, that the DTC, this dual object, which is non-negative, adding to it this stuff, which I want to show is small, is equal to the Shannon entropy of the partition according to my measure mu, plus another term, complicated term, that I know is going to be very small because of the low complexity gradient. This other condition tells me that the second term is also small. DTC is non-negative, so I have this guy plus non-negative stuff is bounded or equal to the sum of two things which are little order of n, so I get this, one page. And I think people in information theory, even if you are not interested in everything I said, you might benefit by looking at this novel chain rule and the manipulation of the DTC, because that might be useful in other contexts. And the paper of Tim Austin appeared in Annals of Probability, which is not a place where most information theorists will read. You don't need to read the whole book, just this paper and just this page, really. Okay, so now just a conclusion. So we covered a lot of ground. What did we say? Constraint satisfaction problem of much interest, a physical representation. Average complexity involve random sparse graph. Detailed statistical physics predictions are given. There are mathematical proofs of some. Moving to the second topic. Naive mean field is a new tool for a class of challenging large deviation problems. Low complexity gradient is a condition related to getting mixtures of product as your representation, which might be nice, and also to this naive mean field approximation, hence to solve these large deviation problems. Thank you.
Beautiful, beautiful. Thank you, thank you. So, any question from the audience? Yes, please. Let me.
Yeah, hi, thanks for the talk. So I had a question about the max cut result for sparse random regular graphs. So you determine the second order term with this per z constant, and then we have the lower order term with, that's like little O of square root gamma. Do you know, like, for moderate gamma, like what the scaling of the constant there is? Like, do we have any control on how that lower order term behaves, other than that it's like little O of square root gamma?
I think a student of Andrea Montanari worked on it, and I think he showed that it's growing like gamma to the 1/6, maybe, but it's still, again, asymptotic. So it's not, so if you ask me gamma 100, this is what I will do. All the results are asymptotic. You lose a lot in the calculation. It's very difficult to do these things precisely. There are in physics actually conjectures what happened for finite gamma, but they are beyond mathematical reach as of now, at least my reach as of now.
Thank you.
Thanks. And any more questions from the audience? I think we still have time for one or two. Any more questions? Oh, yes.
So for the NP complete problems phase transition, so usually we do like a reduction, right, and we can show that all these problems are equivalent in this complexity sense. Is there any hope to do that in terms of these phase transitions as well? Is there some kind of, like, do these reductions kind of hold?
Can you raise your voice?
Oh, sorry. So for the NP completeness part, this dynamic phase transition slide that you had, like, so usually if we do like a reduction from one problem to another, right, like it kind of applies to all the problems for this NP completeness sense.
Right.
But then when you talk about these phase transitions, do those kind of conserve across the different problems? Or is there any connection between the different problems and the phase transitions?
So if I understand correctly, you ask whether for average complexity one can do some reduction from one problem to another, mimicking the reduction procedure done in computer science for worst case.
Exactly,
The
yeah.
answer, number one, this would be extremely interesting to do. Number two, nobody knows how to do it, me in particular, and I don't even know whether it's possible or not. The statistical physics predictions are not based on reduction. They are based on saying this problem and this problem and this problem are all the same. We are going to do the same type of calculus and come up with numbers. The method getting the prediction is the same, but it's not going from one problem to another. It's like doing Euler-Lagrange on different problems, right? You don't reduce, you just follow the same trick or Taylor theorem. So I don't know. It would be nice because it will save a lot of effort. You don't want to see papers 100 page, 200 page per problem. This is ridiculous, but we don't know how to do it otherwise.
Okay, I think we are running out of time, so let's thank Amir again for the excellent talk.